So does this go till 4?
Yeah.
Okay, so it's, and that includes the questions?
Yeah, if you finish around 4 and we can go
okay.
5, 10 minutes
Okay.
for questions. You ready to go?
Yeah.
Okay, welcome everyone. It's my great pleasure to introduce Bharat Ratra from Kansas State University. Bharat started his career as a string theorist, and as he told me this morning, got bored of that very quickly, then moved into cosmology, as so many here have done as well. He toured the US as a postdoc for quite some time, worked in all the famous places, Caltech, Princeton, Stanford, and eventually ended up in Kansas. And within cosmology, he's worked on basically all topics you could imagine, from primordial high-energy physics, primordial magnetic fields, to the sort of more down-to-earth things like the structure of the Milky Way, the distance to the LMC, and things like that. And today he's going to tell us what's the deal with dark energy.
Thank you, Niels. It's really nice to be back at CITA. So there's been a lot going on in cosmology for the last couple of decades, mostly driven by really great new telescopes and really good detectors and fast computers. And we've got two really striking results. I mean, both of them have been around for a while, but I mean, they've been really strongly confirmed. The first is that 95% of the constituents of the energy budget of the universe at the present time are unknown. We don't know what makes up the dark energy or the dark matter. And the other striking thing is that we have pretty strong evidence from cosmological observations that either quantum mechanics or relativity or both have to be improved upon, at least in certain regimes. And so I'm going to talk a little bit about dark energy. And I mean, everybody's kind of heard we're doing precision cosmology now. So I'll start out with the fine print and go back and look at times in the history in the past where people have said similar things. I don't mean to imply that I think the standard, what we call the standard model of cosmology, is going to change drastically. I think we have the skeleton in place, but all the muscles and other things still have to be kind of figured out and put in place. And we can go back to a time in the 1890s, and this is a quotation from Michelson. So he basically says there's not much left to do in physics, and all you can do is precision measurements. And at this point, physics was Newton's 3 laws of motion, Newton's inverse square law of gravity, and Maxwell's equations. And I don't want to leave you with the impression that I'm biased against experimentalists. So I'll give you a quotation from another famous physicist, a theorist from around the same time. And you'll immediately notice the difference between a theorist and an experimentalist. The theorist is much less verbose. So Kelvin comes out and says, there's nothing new to be discovered in physics now. All that remains is more and more precise measurement. And this is kind of a very interesting year, because in the same year, Planck explained the ultraviolet catastrophe in black body radiation and started the development of quantum mechanics. And a few years later, Einstein came up with the special theory of relativity and the general theory of relativity. And so things changed pretty dramatically around then. So I want to start with the summary of the present cosmological energy budget. We know that about 5% of the budget is made up of baryonic matter, and that's the name cosmologists give to stuff that's mostly it's atoms and some charged particles like electrons and protons and uncharged particles like neutrons and stuff floating around. And it's the stuff we see in gas clouds and stars and in blue whales and elephants, what we're made up of. And this number started getting pinned down in the 1960s following the measurements of the first discovery of the microwave background that had sort of been predicted earlier by Gamow and his graduate student and postdoc from their work on the generation of the light nuclei in the early universe. And the measurements were interpreted by Dickey and collaborators at Princeton. It's only been really recently that we've got this number down to about 5%. Even earlier in the 1930s, Zwicky was looking at clusters of galaxies, and he was measuring how fast these galaxies were in orbit around each other. And from that, he could figure out the strength of the gravitational field that was needed to cause these motions. And from that, he could figure out how much mass was responsible for these motions. And he could also measure how much of this mass was shining. It was in the shiny stuff in the stars, in the galaxies. And he figured out that there had to be a lot of stuff that was not shining, that was dark. And at that point, he did not know that it was not made up of atoms, that it was non-baryonic. That came later. But he could tell that it had to be non-relativistic or cold, because if these systems were held together for as long as he thought they were held together, this stuff that was holding them together couldn't have escaped. And it took another almost half a century before we started pinning this down. It took a lot of work by a lot of people. But this is non-relativistic, it's cold, and it's dark. It does not couple as strongly to light as the atoms do. Even more recently, we've discovered something stranger, which is also non-baryonic. It's, however, relativistic. It's moving pretty fast, and it's not bound to the clusters of galaxies. So it's been given a name, a new name. It's called dark energy. I mean, it's not energy and matter in the same sense that this is used in relativity, but that's just a name. And this is what was discovered by the supernovae observations that looked at the acceleration of the cosmological expansion in the 1990s. So basically, we don't understand 95% of the current energy budget. We don't understand what makes up the dark matter or the dark energy. But I hope to convince you that we do have a standard model of cosmology by the end of this talk. And it's kind of really interesting to think about this, and I'm really glad Norm is here. So I mean, if we really want to be unbiased, and CITA is making a really good attempt at this, for every non-cosmologist, every person who's doing any other kind of science, you need 19 cosmologists to be completely unbiased. And I mean, that's dark energy and dark matter is going to be as interesting as atomic physics and stuff like that. It's going to take a lot of time to get there. But I want to motivate dark energy. I'll try to go over that a little bit faster because I know a lot of people here are experts in this. And then I'll focus on two dark energy models, the standard cosmological model with the cosmological constant and cold dark matter, and one in which we have a scalar field phi with a potential that's slowly decreasing as phi gets bigger. That's also called quintessence or scalar field dark energy. And because this parameterization XCDM, where X is the name of the fluid that acts as dark energy, has played a huge role in data analysis. I'm going to talk about that also. But parameterizations tend to be arbitrary, and usually they have more parameters than models like phi-CDM, so they're kind of misleading. So what I'm going to do is I'm going to take predictions from these models and compare to a bunch of observations and try to derive constraints on the model parameters. And then if I have time, I'll talk a little bit about the transition from when the universe was dominated in the past by dark matter to when it's starting to get dominated by dark energy and it starts accelerating. And I'll go on to talk about introducing another cosmological parameter. Hopefully I'll have enough time to do this. So my general motivation is that we're doing cosmology. We're not doing high-energy particle physics. So the data we have is not that great at this point. It's much better than it used to be. But all we can hope to do is constrain maybe half a dozen parameters. And so we've got to parameterize our models in a somewhat semi-realistic way and try to get some constraints on the parameters of the model rather than claim that we're going to get model-independent constraints from the data, which we can't do. And if we have a good model with a few parameters, you can look at, compare different models with different parameters and see if you can conclude that the universe is always accelerating in all of these models at the present time, or whether that conclusion depends on how you parameterize your models, for instance. The other thing you can do is you can compare different data sets using the same model and see if you pick out the same regions in parameter space. If you don't, either your model's wrong or there's systematics in some of your data. And both of those are interesting conclusions, but you'd have to do more work to figure out what's going on. And you can also use models to combine constraints from different data sets if they're consistent. So we know that the universe is expanding. And this was discovered by a combination of Slipher and Hubble and Humason over a decade and a half or so. So Slipher was working at Lowell Observatory, and he studied a bunch of external galaxies. He didn't know they were external galaxies then, but he could measure the redshift of the light from them, and so he figured out they're moving away. And what Hubble did was he could measure distances to these galaxies, and he measured the distances to them. Slipher, from his observations of the redshift, could get the velocity of these galaxies, and Hubble found that the velocity was proportional to the distance. So when you look at a galaxy twice as far away, it's moving twice as fast. And this parameter here is the Hubble constant. It's the present value of the Hubble parameter. And I think a nice summary is about this number here. And Rich Gott and Michael Vogley and I have been working on trying to get an estimate of the Hubble constant for maybe a decade and a half, and we've always ended up at around 67 or 68 from our analysis of different data sets. And it's very, very interesting to me that now most measurements from BAO and from the microwave background, both from WMAP and from Planck, are coming in at this value. So this is an early set of data that shows you the Hubble law. So on this axis we have the recession velocity. On this axis you have the distance to the galaxy you're looking at. So there's a galaxy over here at 100 megaparsecs. It's moving away at 7,000 kilometers a second and so on. And this is the Hubble law. And so this is the expanding universe. So let me just take a little bit of a detour here. So I said that I kind of favor this value of about 68 plus or minus 2.8. And there are other measurements that use the HST and Cepheids and Mazars that are coming in a little bit higher, around 74. And so what we've looked at here is allowing the number of effective neutrino species to vary and using different priors for the Hubble constant, either this value or this. And if you look at the blue contours, they're over here. The red contours are over here. And the standard model of particle physics kind of favors, for n effective, about 3.046. And I find it kind of interesting that the standard model of particle physics favors a Hubble constant of around 68 over 74. So if you don't want to introduce dark radiation, you kind of pick out a slightly lower Hubble constant than people had used previously. Okay, so we have an expanding universe, so you have preferred observers, so you have to be a little bit careful about how you phrase everything. So we're going to phrase them in terms of these observers called the cosmological observers that are at rest with respect to the expansion. And we're going to assume the cosmological principle, which is pretty well tested, at least the isotropy part, that it's isotropic for pretty much any cosmological observer, and then you're forced to spatial homogeneity. And with homogeneity, you can only have 3 possible geometries for space. And so I've written the line element up here, and I've suppressed one space dimension. We have the closed models, this just is like the surface of the sphere, or the open models, the surface of a hyperboloid that goes out to infinity in all dimensions, or the flat models that are Euclidean. And omega is greater than 1 for the sphere, less than 1 for the hyperboloid, and equal to 1. That's the density parameter. And the curvature parameter is positive, negative, and 0. So these are the 3 options. And you need an equation of motion for the scale factor, which in a very loose sense you can think of as, say, the radius of the sphere. And that's a large part of what you want to do with cosmology to start with, is to figure out how the expansion goes as a function of time. So you've got to derive some equations, and they come from the Einstein equations for general relativity. And I've written down the simplest set over here with the expansion law, the Hubble expansion is A dot over A, where A is the scale factor and the dot is the derivative with respect to time. That's driven by gravity, so you have big G from Newton's constant for gravity, and the energy density for whatever fluid you have here. You can write this down for any other substance like a scalar field, but I'm just going to write it down for a simple fluid. You have a contribution from space curvature and a contribution from a possible cosmological constant. So to complete the system of equations, you need to know how rho varies with scale factor or time. And for that, you need the stress energy conservation equation. So that's this equation, and that introduces pressure. And to complete this system, you need an equation of state for the pressure. So these are the 3 equations that we can keep in mind when we're thinking about what's going on here. So we have the expansion rate, which is A dot over A, and we know this is positive because the universe is expanding. Hubble and Slipher told us that. And the next obvious thing to do is to take a time derivative of this and find out whether it's increasing or decreasing with time. So is expansion accelerating or is it decelerating? And a way to phrase that question is to use these equations and try to get an equation for a second time derivative of the scale factor. And so that's the thing I've written down over here. So this is A double dot divided by A equal to something on the right-hand side. And this combination, rho plus 3 times the pressure, is what's known as active gravitational mass density, because pressure here measures the kinetic energy, and we know that the kinetic energy through E equal to mc squared, E is equal to mc squared, can act as a source of a gravitational field, and that's the relativistic part over here. If I'd put in back my powers of c, I'd have a c squared in the denominator, and that would go away in the non-relativistic limit. So we have a minus sign here, and if we kind of think about this for a minute, set the pressure to 0, so stop your galaxies from moving, let them all be at rest with respect to the expansion, just going along with the Hubble flow, then the only source for the gravitational field is rho. And you only have positive mass. And with this minus sign here, you make a prediction that for normal matter, the universe is going to decelerate because A double dot is negative. And you can try to go out and measure this. And if you find A double dot is positive, you have a problem, because rho cannot be negative to cancel that minus sign. And your only option is to introduce some kind of material with a strange equation of state, where the pressure is large and negative and overwhelms the positive part of rho. And that's what dark energy is. Of course, this is kind of, I mean, we really need to write down the equations of the stress energy tensor and put in a scalar field with a potential, for example. I mean, there are substances that do have negative effective pressure. And we see this also in the lab too with things like the Casimir effect or the Lamb shift. And one hopes that a similar sort of thing on cosmological scales where you introduce what's known as a cosmological constant or a scalar field with a certain potential can cause you to have negative pressure. Okay, so I want to start looking at the various contributions, and I'm going to use another system of units instead of working with everything in terms of grams per cubic centimeter. I'm going to introduce this density parameter where I measure all the rhos relative to the critical energy density for the Einstein de Sitter model, which is the model in which this term and this term are 0. And then rho is completely determined by the Hubble parameter. And that's just a new system of units. That's the omega parameter. So dark energy, most people know this. It's, I mean, the way you go about looking at this is to compare the expansion rate at different times in the universe. And so I've put down two universes here, the Hubble law in a universe that expands slowly and one that expands more rapidly. And if I look at a galaxy at a distance d away from us in these two universes, in the one that expands more slowly, it's moving at a slower speed away from us compared to one where it moves at a more rapid speed away from us. So what you want to try to do is measure this expansion rate as you go back in time. So as you're going out further and further in distance, you're going back in time, because the signals that you see from a galaxy over here took much, much longer to get to you than one from over here. And so you want to try to do that and compare the expansion rate at early times or large distances with the expansion rate at later times or small distances from us. And then there are really only three options. You could have a universe that expands at a constant expansion rate, that's the purple line, or one that expanded more slowly in the past, like the blue line, and then it came onto the purple line over here, so the expansion has sped up. This is an accelerating universe. Or the opposite option, where it expanded more rapidly in the past as you go further back, like the green line, and then it slowed down as it got to you. So to figure this out, you want to measure the expansion rate over here and over here. So if you want to measure the expansion rate over here, you're looking at objects that are really far away. And so you've got to look at really bright objects. And in the 1990s, the brightest objects around that we understood were the type 1a supernovae. And that was a great breakthrough. So when people did the supernovae observations, they all landed up on the blue side of the plot. And we've all seen plots like this and plots like this also, which is about 10 years old, although the contours haven't changed that much. The big difference has been that the statistical errors have shrunk a lot and the systematic errors have kind of expanded a bit. And so the supernovae prefer a region in this part of parameter space where this is the density in dark energy, and in this case it's just a cosmological constant. And on this axis is matter, including dark matter and baryonic matter. So we're roughly about 3 sigma away from 0 dark energy, which would be down over here. And that tells you from the acceleration equation, you need a substance with a negative pressure, a significant negative pressure, and that's dark energy. So this has been around for a decade and a half. So what do we know about dark energy? One obvious thing is to try to check whether it varies in time. I mean, is it just a cosmological constant, which would be very, very difficult to understand from first principles, or does it vary with space and time? And when you try to approach a question like this, you've got to understand the assumptions that go in. So we're assuming that the general theory of relativity is correct. We're assuming this equation is correct. And it could be that this equation is wrong. But it seems to me that that's less likely to be true than the fact that the right-hand side of that equation might be a little bit different than what we think is on the right-hand side. The other thing we have to worry about is whether the astronomers have really understood all their systematic errors. And it seems to me there's been so much work on the supernovae that all the groups agree to within better than 1 sigma. And there's a lot of supporting evidence from the microwave background, if you assume certain models that are motivated by other things, that you can get a number for the dark energy that agrees with the supernovae. the BAO measurements also agree with this. So there's a lot of observational support, and probably we're not going to have the dark energy disappear because of systematic effects. So if we want to try to answer a question like this, we need to construct a couple of models and see which one fits the data better. So let me start by introducing a few models, and I'm going to show you a bunch of plots like this. So what I'm going to plot on this axis, and they're both going to be log axes, I'm going to plot the energy density of the constituents of the universe at relatively late times as a function of the scale factor. So I'll start with the standard model, the lambda CDM model. And in this model, on the right-hand side of the Friedmann equation, you have a contribution from whatever forms of energy density you have. I'm putting all the matter in here, baryons and dark matter, possible contribution from space curvature, and a possible contribution from a cosmological constant. The cosmological constant doesn't change with time. That's the green line. Space curvature, the energy density drops like 1 over a squared. That's the orange line. And baryons and dark matter drop like 1 over a cubed because it's just the volume dilution. The rest mass energy is what contributes. So it's the rest mass divided by the volume. So as time goes on, you initially start with a dark matter and baryonic matter dominated epoch where the expansion decelerates because P is basically 0 and rho is positive. Then you switch to a curvature-dominated epoch, and then you come over to the dark energy-dominated epoch with the cosmological constant, and the expansion accelerates at the present epoch. So there's one constraint on this. You'd think that 3 free parameters in this model, but there's actually one constraint that the sum of the omegas has to add to 1. So you only have really 2 free parameters. And conventionally, what one uses is the energy density parameter for the matter at the present time, and that in the cosmological constant. So the problem with a model like this, at least as some particle physicists see it, is that you can measure the energy density in dark energy now, and that's an energy per unit volume, so you can convert it to an energy scale and take the 4th root, so it'll be basically the 4th root of this in natural units, and that turns out to be a few millielectron volts. And that's disturbing to some particle physicists because that's a new fundamental scale that characterizes the universe, and that's sort of the scale at which chemistry is relevant. And it seems a little bit difficult to understand why we have this new fundamental scale. And the only scale in particle physics that might be relevant is a neutrino mass scale of a few millielectron volts. And so maybe dark energy has something to do with massive neutrinos. The other option is that this scale might not be generated at the present time. It could be that it was slightly time varying. And if you had enough time, your fundamental scale could be set in the early universe, and as time goes on, it would drop to a millielectron volt now. And this is similar to the reasoning that Dirac used to explain why gravity is so much weaker than the other forces. He basically says big G changes with time. The universe is really old, so you can have a tiny changing G, and that could give you a much weaker force now, and gravity was as strong as the other forces in the early universe. So we're trying to do this with dark energy, so we just kind of bend this up a little bit. And there's a bunch of ways of parameterizing this, and the most common parameterization just introduces another fluid. So to keep life simple, I'm going to take a spatially flat model. This is what's known as the XCDM parameterization. And I'll introduce a fluid, or rho sub x, with an equation of state. And if you go plug into that acceleration equation, the acceleration Friedmann equation, the A double dot equation, you'll see that the equation of state parameter, if it's less than minus 1/3, if rho is such that the pressure is enough to overwhelm it and it's negative, then you get the substance behaving as dark energy. So basically, it gives you an accelerated expansion. So you go from a matter-dominated epoch to a dark energy, a time variable dark energy dominated epoch over here. And that's how the equation of the energy density in this X fluid changes with time. So because I've made this spatially flat, there's really only 2 free parameters. And the two free parameters I use to parameterize this model is the density of matter at the present time and the equation of state parameter for the X fluid. So this is an incomplete model. It's a model with a fluid with negative pressure, and we know what happens when you have a fluid with negative pressure. It's unstable. So the moment you start doing perturbations of this model, they're going to grow exponentially fast, and you're going to end up with something that does not look like the real universe at all. So you cannot do perturbations. You cannot talk about, say, CMB perturbations in this universe. You've got to modify it. And so that's what makes it a little bit disturbing that a lot of people use this for data analysis when it's not a consistent model. So what we were motivated to do is to kind of look at a more consistent model for a time-varying dark energy. And we thought maybe we should introduce the scalar field. And see, a Friedmann equation becomes a little more complex. You still have the energy density contributing to that, but now you have an equation of motion for the scalar field, a Klein-Gordon equation in the expanding universe. So phi double dot plus the Hubble drag term times phi dot and the derivative of the scalar field potential. And we introduce a scalar field potential that's maybe a little strange to most particle physicists. It's phi to the minus alpha, where alpha is a positive constant. And that gives us some very, very nice properties. So what happens here is that at early times, the matter distribution, matter density dominates, and you get a matter-dominated epoch with decelerating expansion. And then the scalar field potential kicks in, and the scalar field energy density overwhelms the matter energy density. And if you choose alpha appropriately, you get an accelerated expansion here. The really interesting thing about this model is that with a potential like this, you can solve these equations, and you find that there's an attractor solution that makes the scalar field energy density behave in a very, very nice way. It takes the energy density and it looks at what's driving the expansion of the universe, and the scalar field then decides that it wants to overwhelm that. So it always wants to come and increase relative to the dominant source of energy density. And so maybe this can explain partially why the cosmological constant or the dark energy is dominating at the present time, which is something that's very difficult to understand when you just have a cosmological constant where you just have to adjust the cosmological constant up or down. So in a model like this, your fundamental scale is set way back in the past, and it could be TeVs or 10 to the 10 GeVs or whatever you want, depending on your fundamental particle physics model. And as time goes on, because the scalar field energy is driven down, it comes down, and then it slowly wants to overwhelm the other energies. And so you get back your scale of a millielectron volt now. And so that's not the fundamental scale that you're introducing in this model. OK, so what I want to do is look at these models and make some predictions. And I've just picked a few data sets. It's a little bit difficult doing the CMB anisotropy in the phi CDM model, so I'm not going to talk about that, but I'll look at type 1a supernovae, baryon acoustic oscillations, Hubble parameter as a function of redshift, and the growth factor as a function of redshift. So for instance, for the Hubble parameter as a function of redshift, so basically you want to compute something that depends on the parameters of the model. And it's useful to give it in terms of the redshift, which is related to the observed wavelength of the light compared to the wavelength of the light you would get from that same transition in your lab. And that can be related to the scale factor at the present time and the scale factor at the time at which that light was emitted that you detect in your telescope. So it's useful to rewrite the Friedmann equation in this form, where the Hubble parameter squared is equal to the Hubble constant squared times this function here that I'm calling E squared of Z and P. And for the lambda CDM model, you get the contribution from omega matter. It goes like 1 plus Z cubed omega space curvature, 1 plus Z squared, and the cosmological constant. And there's this constraint at Z equal to 0 if you evaluate this at 0. So the free parameters I'm going to choose for this model are omega matter at the present time and omega lambda. And so we can predict H as a function of the redshift and the free parameters of the model and H naught. and then compare it to observations however you want, whatever technique you want to use. And I'm going to do this for a bunch of data sets and a bunch of models. So let me just spend a little bit of time on plots like this. I'll show you a lot of them. So this is for the lambda CDM model. This is for the XCDM parameterization. This is for the phi CDM model. And for lambda CDM, these are the two free parameters. It's omega lambda and omega matter. For XCDM, it's the equation of state parameter for the X fluid and omega matter here. For phi CDM, it's the constant, the index of the potential, alpha, and omega matter. And what I'm showing you here is the best fit value. This is from the type 1a supernovae, the best fit value. And 1 sigma contours, 2 sigma contours, 3 sigma contours, 1, 2, and 3, and 1, 2, and 3 outwards. So this is a spatially flat model. Any model that lies in this line is spatially flat because omega matter plus omega lambda adds to 1. And if you're over here, you have accelerated expansion. Down over here, you have decelerated cosmological expansion at the present epoch. And over here, you have these bouncing models. There's no Big Bang for the lambda CDM, so that's not of interest for us. So we can see that a model with omega matter of about 0.3 and omega lambda of about 0.7 fits the data really well. But there's a big range of models that fit the data, including some models that are decelerating. That's like 2.5 sigma. So in the XCDM parameterization, a model with omega x equal to -1 is the same as the models that lie along this axis. So that's the flat lambda CDM models. And again, that's the favored point, omega matter of about 0.3. And here it'll be omega lambda of about 0.7. For phi CDM, we're down here on the axis at which you get the flat lambda CDM models because alpha is 0. And so that's the favored point. But there's a lot of space where you can have time-varying models within 1 sigma of this. And the same thing's true here. A lot of these models have time-varying dark energy. So lambda CDM, the standard model, is a really good fit to the data, the supernovae data. And a lot of time-varying models also fit the data. So I'm going to run through a bunch of different data sets. So I'm going to look at baryon acoustic oscillations. And the contours shift around, so that's what makes this really interesting. They're not all in the same direction in parameter space. So we get a model with omega matter of about 0.3, omega lambda of 0.7, standard lambda CDM. It fits really well. The same's true over here and over here. But there's a lot of space for time-varying models. You can have a wide range in alpha. So none of these data sets rule out time-varying dark energy. So this is Hubble parameter as a function of redshift. So there's about 28 such measurements. And here it depends on what value of the Hubble constant you use to analyze your data. So there's two sets. There's the solid lines that use 68, and the dashed dotted lines use about 74. And you can see that they move around quite a bit here, depending on what Hubble constant you use. So you have to pin down parameters like the Hubble constant if you really want to pin down your cosmological parameters. But again, in both cases, a model with omega matter of 0.3 and omega lambda of 0.7 fits the data really well. And it doesn't matter whether you use XCDM or phi CDM or lambda CDM to analyze the data. You can do this with many, many different data sets, and you end up pretty much at the same conclusions. This is the growth rate, so how fast cosmological structure grows as a function of redshift. And again, a model with omega matter of 0.3, omega lambda of 0.7 fits the data very well. And it doesn't really matter how you analyze this, what parameterization you use for dark energy. OK, so the constraints from the different data sets are not inconsistent. So we don't have any big problems. And they all are happy with omega lambda of 0.7, omega matter of 0.3. That is with the spatially flat lambda CDM model. But they don't rule out time-varying dark energy. So the next thing to do is obviously just combine data sets 2 at a time. And I'm going to step through this again. So the only difference is that the range in parameter space now shrinks. And you're getting tighter and tighter constraints. So this is 2 data sets, supernovae and BAO. So again, a model with omega matter of 0.3, omega lambda of 0.7 fits the data. It doesn't matter what parameterization you use to analyze the data, but they all work. You can look at Hubble parameter and BAO. And here you start seeing the bigger differences due to the uncertainty in H. So the contours move around quite a bit depending on what H you use, H naught you use. But again, a model with omega matter of about 0.3, I mean, it's starting to get to be like a 1.5 or 2 sigma off, but it's not that big a deal depending on what data set you use. A BAO and growth factor and Hubble parameter and supernovae. So I'm not going to conclude, give you precise measurements of the cosmological parameters, but let me start kind of winding down here a little bit. So when you combine the data 2 at a time, again, a lambda CDM, standard lambda CDM fit the data really well. But the data, I mean, even though they're more tightly constrained time involving dark energy, they cannot rule it out yet. So we need better data. So there's a bunch of issues that need to be dealt with. So I just focused on one type 1a supernovae data set. But there's about half a dozen of them. And depending on which one you use and who you talk to, the contours move around by half a sigma. So we're not yet at the level of doing precision cosmology. You can see the same thing if you look at GRB. The people now have techniques to standardize GRBs. And depending on what technique you use, you get slightly different constraints on the parameter values. What you use for H naught changes things by maybe half sigma. And in some cases, you can see with omega baryons too, that it changes things by half sigma depending on what you use. So I mean, everybody sort of realized this, that we need better and much more data. And this is going to happen pretty soon in the next 5 to 10 years, especially with experiments like DAISY and Euclid, where we're going to get much better BAO data, which seems to be the cleanest right now. So I'm going to take a little bit of a detour here and see if we can conclude anything that's sort of model independent. And what I'm going to look at is the HZ data as a function of redshift. And so I've plotted on this axis HZ divided by 1 plus Z, and we'll see in a second why I'm plotting that as a function of redshift. And there's about 28 data points here. And I've just drawn, there's 6 best fit models here, lambda CDM, X CDM, and phi CDM, and with the 3 different H naught values over here. And I've drawn 3 sigma discrepant models. So these models are favored by 3 sigma over these 2 models. And so you can actually see that there's a transition from decelerating cosmological expansion over here when the universe is dominated by dark matter and baryonic matter to accelerating cosmological expansion over here. And to see this more clearly, we can bin the data. And we see this here, that the data suggests this transition here. And in this lambda CDM parameterization, when you go to high redshift, this term is going to dominate over these 2. And so you see that over here. And as you go to low redshift, this is the term that dominates. And you see that over here. And you're seeing the transition. You can measure the redshift of this transition. It's about 0.74 plus or minus 0.04. And that's a really nice number. It's telling you where the switch occurred. And it's consistent with what you get just from the lower redshift data for these models. So we're finally seeing this transition from a matter-dominated epoch at earlier times to a dark energy-dominated epoch at present times. But it's not, we don't have enough precision to distinguish between these different dark energy models. And that's going to happen probably in the next 5 or 10 years, that the measurements will improve a lot. OK, so a lot of these models I've looked at have zero space curvature. And that's motivated in part by the CMB data. But we've got to remember that the CMB data assumes that the dark energy density is time independent. Most of it's based on the lambda CDM model, but if you put in a model like XCDM or phi CDM, then you don't get as tight a constraint on space curvature. So I want to look at these other data sets in the context of models that have space curvature too and time-varying dark energy. So I'll put space curvature back in the open CDM model. So we go from decelerating expansion when you're dominated by matter to the space curvature dominated epoch and then accelerating expansion. And you can do the same thing in phi CDM. And again, after a lot of work, we were able to show that you get the same attractor solution in these open and closed cosmological models when you have this phi CDM potential of this form. So we can look at these data sets again and just look at supernovae BAO and HC. I'll just combine them. So this is for the XCDM model with curvature, the phi CDM model with curvature. The dotted lines, this is the kind of plots I showed you before, omega matter, omega x, omega matter, and alpha. The dotted lines were the constraints we got from supernovae BAO and HC before. And when we put in space curvature, the contours get stretched in the direction in which the parameterization tells you dark energy is varying with time. The same thing happens over here. The contours get stretched this way. Once you introduce space curvature, it's much more difficult to constrain the time-varying part of the dark energy. And there's quite a bit of space if you look at the other slices of parameter space. So this is just something that seems interesting. I don't know if there's any real consequences. We've got to see the CMB also, because that's where the tightest constraints come from. So I'll start summarizing now. So I hopefully have convinced you that we have a standard cosmological model. I mean, we don't know what the dark energy is. We don't know what the dark matter is. I mean, it could be a cosmological constant, or it could be phi CDM. And I think GR is OK. And the problem is with the T mu nu. And I also think the astronomers have pretty much got a good handle, but there's still some work to do. The main issue I think that people need to look at a little bit more, and a lot of people have been looking at, is whether it's fair to say that a time-varying dark energy only couples through gravity to the rest of the universe, or whether there's other, say, weak-scale couplings, or even weaker than that through to, say, dark matter, for instance. And that makes things much more complex because you could introduce many, many different kinds of couplings. And so I'm not quite sure how progress is going to be made there. For dark matter, I mean, it could be something that's left over from supersymmetry or from QCD. It could be axions. And maybe in the next few years, we'll hear something from CERN or one of the underground searches for dark matter. And maybe we're already getting suggestions from a bunch of astrophysical observations for the abundances of small halos around big halos, or nuclear profiles, both galaxies and in clusters, that maybe pure cold dark matter doesn't work. And maybe one thing to do is couple dark matter to dark energy and see if that improves the observations enough to motivate it. So once you guys have resolved all of that, here's a few more things left. So in case you thought cosmology was over, I'll leave this up for a second. And just conclude. Thank you.
Other questions? Yes.
When you put on the question at the end, is general relativity correct on larger scales? Are you suggesting that we should consider MON?
That we should consider?
Modified Newtonian dynamics.
Well, MON probably is not going to do you that much good on large scales, but people have these other modifications of GR, especially designed to do away with dark energy. MON probably is not going to work too well because, I mean, my understanding is that it reproduces the rotation curves of galaxies really, really well, but the critical acceleration is galaxy dependent, and it would seem to be a little bit strange that you have to have such a fundamental parameter that changes from galaxy to galaxy. But people have looked at other modifications of general relativity and tried to get rid of dark energy. I'm not sure a modification of general relativity is going to get rid of dark matter, because it's mostly Newtonian gravity that's relevant there. But we know that dark modifications of general relativity in large scales would seem to be, at least to me, probably not the way to go, because the microwave background perturbations are reasonably well described by assuming general relativity. I mean, you're talking about a factor of 2 or 3. And we know general relativity works on really small scales really well when you discuss gravity wave emission from binary pulsars. And it would seem to me strange if GR just broke down on scales at which you see cosmological expansion, but it worked reasonably well both on small and large scales. But that's my opinion.
So one question that I had is related to this quote. So you've basically shown us that all the models that you tested are possible.
Well, a large region and parameter space of each of the models.
Have you tried to quantitatively rank them in any way?
Not really.
You could ask which is the preferred model.
Well, I mean, probably it's lambda CDM because I mean, seems the simplest, but I don't know.
So what's it going to take for you to say time varying dark energy is ruled out?
Probably with. I don't know. I mean, it depends, right? I think with the next generation, if Daisy and Euclid perform as well as they perform, then probably we're going to maybe abandon time varying dark energy if they're really consistent with lambda CDM. And I mean, we can go to even higher redshift if it's really possible to standardize gamma ray bursts. So you could go to redshifts of 5 and 6. And it might be really interesting to try to do that and see if they agree. But if pretty much anytime you analyze a data set and lambda CDM is consistent with it, then probably you're not going to be motivated to go look at time varying dark energy. But I mean, at least from a theoretical point of view, it seems somewhat difficult to understand cosmological constant. I mean, it would be nicer if it was a dynamical field.
So what connection do you see, if any, between early inflation and late inflation?
That's what it was one of our motivations. And we just tried to kind of bend the inflation potential over. So your early, if you just draw the potential here, V of phi, the function of phi, inflation used to be something like this. And then you'd have just a tiny bit left over here. So what we try to do is just do it like this, so that you can have a tail where you have dark energy now, and the scalar field just rolls down, and when it steepens, it reheats. And in our model with the phi to the minus alpha, the constraints on alpha are a little bit too tight now. We had thought that you could drop the energy per unit volume just. Yeah, where you steepen the potential enough that you can reheat it and just do it fast enough that way. I mean, we don't have a model for that or anything, but that's kind of what's our hope. And I'm not sure people understand reheating well enough to really discuss models at the appropriate level yet. But we had tried to drop, so it depends how you do this fine-tuning estimation. So the normal way people say is it's 120 orders of magnitude, and that's the ratio of the energy density from the Planck scale to what you measure in the cosmological constant now. And if you turn that into just a ratio of energy scales, it's about 30 orders of magnitude. So we had hoped to reduce that to maybe the same level as the Higgs mass fine-tuning. But it's probably a little bit more difficult now because alpha has to be close to 0. So to get a nice ratio here, we'd need an alpha of about 3 or 4. and that's inconsistent with the present observations. So you could have an alpha of 1 or so, and so you still need, what you're getting is something that drops like this. And so there's still some pretty big drop, but not as big as dropping it down to over here and getting it to do that. So it would be nice if we just had to introduce one scalar field that did inflation and dark energy.
Right. Are there other version questions?
What are you going to do? Anything with CMB data?
Yeah, we're going to try. We're working on trying to do the CMB.
All right. That's it. So there should be cookies upstairs. So we can
Great.
continue the discussion there. And let's thank Bharat again.
Yeah.
I should mention we'll be taking Bharat out for dinner tonight. So if you'd like to come along, just let me know.
The idea for the repeating was it would occur right at this discontinuity section.
Yeah.
Yeah.
So how do I switch this off? Just press this?
I don't know.
Okay.
Someone will come and take care of it.
Biggest bombing of the Soviet Union.
Yes.